review that we spoke of subatomic particles on day 2 of last week. Protons, neutrons, and electrons. You need to know that the protons are positive and neutrons are neutral, and that both of them have significant mass, whereas electrons are negative and have very little mass, which means that the structure of an atom is like that, with the neutrons and the protons in the middle, and the electrons buzzing around the outside. And that it's those outer or valence electrons that are really the kind of the business end of an atom as far as we're concerned, since we're mostly going to be concerned with chemical bonding, right? Bonding being kind of the meat and potatoes of chemistry, forming and breaking bonds, chemical reactions, and covalent bonds, where electrons are held more or less equally in a pair between two atoms. That's the kind we're going to need to be dealing with mostly this chapter. So, here's the part where we narrow everything down a little bit because this is biology. It's kind of nice. Grab that periodic table. It is on page 42 of your student agenda. Remote learners, you're going to want to get a periodic table from somewhere. I'm not sure if you have agendas or you can just print a periodic table off from the internet. That's also fine. There's probably one in your digital textbook somewhere. So it turns out that 96% of your body is just 4 of those elements from the periodic table. 4. In fact, 96% of any living thing, not just humans. Trees, insects, bacteria, bread mold. 4 elements. And here's where we come back to Lewis dot structures, which maybe you tried to learn last year, and I promise you is easier this year. Someone want to give me one of those 4 elements? Do you know what they are? Since you did your homework, Tate, what's one? Nitrogen. Good. Nitrogen is one. Hydrogen is one. Good.
Oxygen.
Oxygen. And finally, what's that last one? It's the one we're going to talk about almost exclusively today. It's the one that there's a whole branch of chemistry to talk about.
Carbon.
That would be carbon. Good. So, if you want an easy way to remember that, first of all, do you know about columns in the periodic table? Do you know about the Roman numerals in the periodic table? Oh, they're good, because we want to know how many outer electrons an element has, right? Well, that Roman numeral column in the periodic table tells us exactly that. If you look, find carbon. Do you see, you know what I mean by Roman numerals, right? Under the regular number that's there at the top. What Roman numeral does carbon have? You can read Roman numerals, right? What does IV mean? It's 4, which tells us exactly how many outer electrons carbon has. So those 4 elements, hydrogen, oxygen, nitrogen, and carbon. And if you're looking for a dumb way to remember this thing, if as I always am, it spells honk. Kinda. With a C instead of a K. But that's not enough. Just knowing how many outer electrons there are does not tell us how many covalent bonds each of those atoms can make at once. And that's what we're really after. That's what Lewis dot structures are all about. Finding out how many bonds those things can make at once. How many single, lonely, unpaired electrons they have. We're going to need that information from the column number. The 1, the 6, the 5, and the 4. And we use Lewis dot structures to turn that into an answer. How many bonds can it make at once? So here's my 3-minute lesson on how to do Lewis dot structures, because it really doesn't take any more than that. It really doesn't. First of all, you write down the symbol of the element you want to do the dot structures for. We've taken care of that. Second of all, you got to know how many outer electrons it has. We got that covered. Third, though, in your brain, don't draw them, but in your brain, you want to put 8 spaces around the atom, little holes for electrons. There's 8 of them, and there's 2 to a side. Think of it like a box, right? Think of it like there's this box where 8 electrons can go. The box you draw around the element, but you don't actually draw those holes. You just know they're there. There's 8 spots electrons can go. Everybody with me so far? Well, then you got this, because it's literally, there's only one more rule. And it's a very simple rule. And the rule is they don't pair up, the electrons don't pair up on one side of the box until they have to. So, well, it's kind of a non-issue for hydrogen, right? Because there's only one. So we put the dot on whichever side we want of hydrogen. Good. Oxygen gives us the lesson, though. Oxygen, think of those 8 spaces. Doesn't matter where you start, but you go around the box one side at a time, one electron at a time, until you have to start pairing them up. So it looks like this. 1, 2, 3, 4. I've done 4 of the 6 electrons. Now I start pairing them up. 2 on one side, 2 on the next side, and I'm done. Well, what does that tell me? That tells me that oxygen can form how many covalent bonds at once? How many covalent bonds at once? How many single, lonely, sad, unpaired electrons? 2. Yeah, which means, hydrogen can come along and get cozy here and share its electron, and here and here. This is like I showed you last week, and that's how water gets formed, right? Do you get it? That's the 3-minute lesson on Lewis dot structures. To see if you get it, why don't you go ahead and do nitrogen for yourself. And then go ahead and do carbon. Did I say do both? Do carbon too. Okay, you got it? This is easy, right? Tristan, tell me how many covalent bonds nitrogen can form at once? 2? Tell me how you got that. So you had 1 pair, right?
Oh, yeah.
And then how many singles?
3.
So how many bonds at once?
3.
3, not 2, right? It goes 1, 2, 3, 4, and 5. So nitrogen has these 1, 2, 3 single unpaired electrons that it can form bonds with. How about carbon? Yuri, how many bonds can carbon form at once? 4. We didn't have to pair any up, did we? Just 1 to a side, just like that. And that right there is kind of carbon's superpower. there are very few elements that can form 4 covalent bonds at once. It's kind of like the best Lego piece in the box. It's that one you're always hunting for, you know, the sound of hunting through a Lego box. It's very distinctive, right? It's kind of like stirring up mac and cheese. You'd never mistake that sound for anything else. It's the hub. It's the one that lets you join different stuff together and make super complicated molecules. So much so that there is an entire branch of chemistry devoted to the chemistry of carbon-containing molecules. It's called organic chemistry. And organic simply means, in chemistry terms, organic means carbon-containing, or more specifically, molecules that have carbon-carbon bonds in them. Like I said, carbon's kind of the ultimate Lego piece. Its 4 bonds at once mean that you can build crazy complicated stuff with it. In fact, pretty much every complicated molecule you are built from is built on a backbone of carbon. Lots of other stuff stuck to that carbon backbone, but the backbone is what enables those molecules to be so beautifully branching and complex and looping, and there's rings of carbon, there's huge branching chains of starches, endless code in DNA and RNA, all built on that carbon backbone. And so, in the space movie where the alien comes up and says, "Attention, carbon-based life form," it is absolutely true. Life on Earth is carbon-based. Questions so far? Organic chemistry, by the way, in college for science majors is often one of those weeder courses. If you've heard of those, the ones where that's where you find out who's really going to be a science major and who's not, because it's hard enough that if you're not serious about it, you're not going to do well. But it's such cool stuff. Like for me, it was the first time I ever really appreciated chemistry, because it was like the chemistry of the stuff that I liked, living things. The other cool thing about it, and I'm just going to give you a taste of today, is the naming systems in organic chemistry. You start to learn those and you start to realize that you know exactly what the molecules look like in, say, the ingredient lists on the back of your favorite foods, or the fuel can in your shed. You know what those look like. So let's do that. Let's talk about naming in organic chemistry. And here's where you're going to need your computer as well as your notebook. You're going to go ahead into Classroom. And you're going to find the link at the top that says Molecular Modeling Online, which will take you to this. Yeah. There's one right there. In the future, please get them from your first period class and carry them all day. It's in that cap right there. Ordinarily, by the way, this would not be online. We would be using these little baggies. We'd be sharing them with a partner. Then the next class would be using them. They just don't have enough. You'd have to share them from class to class, and it would be real hard to disinfect these suckers. So, online it is. There may be a day when I have divided stuff up enough that you can use the physical models, but this is almost as good. For example, can you tell what atom you're looking at? It's actually 5 atoms. The gray one in the middle and then the white ones are covalently bonded to it. So knowing what you know about how many bonds things can form, what's the gray one in the middle? That's carbon, absolutely. That's carbon. And the white ones that only have one bond, what's the one that only has one? That's hydrogen. So what you have here is 4 hydrogens bonded to 1 carbon. Now, turns out the way we name that, first of all, if it's just hydrogen and carbon and there's no double bonds, the ending we use is ane, A-N-E. The prefix we use depends on how many carbons. And when there's just one, believe it or not, the prefix we use is meth. Anytime you see the prefix meth, what it's referring to is little 1-carbon chunks. So what's on your screen? What molecule is that? Methane, absolutely. Methane, which is a gas at room temperature, which is flammable, and which is a really common product of organic decay. In other words, when things that were alive start to break down. And so it's what comes out of the rotting stuff at the bottom of swamps. It's what comes out of landfills. It's why they have to pipe the gas out of landfills so it doesn't explode. And they actually use it sometimes for fuel. And believe it or not, it's what comes from digestion in the intestines. It is a gas that is a significant part of intestinal gas. In other words, what you got on your screen right there is basically a fart. Congratulations. Add a carbon. Can you figure out how to do it? Click on a carbon in the upper left. Click on the carbon icon, and then click on one of those 4 hydrogens. Like this. I think you can also drag, but it seems easier to click. And the nice thing is it fills the hydrogens in for you. If you were building here, you'd be going nuts getting all those carbons on there, because carbons do kind of naturally fill empty bond spaces. And so same thing, this is an ane, but we changed the name of it because it's 2 carbons long. It is now not methane, but ethane, E-T-H. Oh, this is killing me. I'm sure there's an easier way to do this. Ethane. Also a flammable gas, also common in decomposition. Add 1 more carbon though, and now we're into fairly familiar territory. Do you know what the prefix for 3 carbons is? Are we talking about a molecule you're familiar with? What is it?
Propane.
What's propane? You've probably got a tank of it in your backyard, under your grill, right? Very commonly used portable fuel. Add a carbon, 4 carbons, and we're looking at butane. Lighter fluid. That's what that is. So that is a little taste of the naming of simple hydrocarbons, which is kind of the basis of naming more complicated molecules. It's always going to start with how many carbons are there, and is it just single bonds between the carbons, or are there double or triple bonds? If there's double bonds, then we're going to call it an ene rather than an ane, and if there's triple, it's going to be an ine. That's Y-N-E. We don't have to worry about that. If you know these, plus the functional groups I'm about to talk to you about, you're good. Any questions so far? All right. So, functional groups. Functional groups are we take our carbon backbone and we add some other atoms to it. And there's certain groups of atoms that you can add that not only change the name of the molecule, but change the function of the molecule, change the properties of the molecule. Okay? Once you're caught up, get into your modeling simulation. And add, doesn't matter where, one of the hydrogens, add an oxygen. Hit the O, and then click on one of those hydrogens. And it's going to add an oxygen, and then it'll automatically fill the extra spot with a hydrogen. You're still on your 2-carbon base, right? You should have 2 carbons, all filled in with hydrogens around them, except in one spot. And that spot should have an oxygen sticking out. With a hydrogen on the end of it. So what you just did was you added a functional group called a hydroxyl group. And a hydroxyl group, when you add it to a simple chain of carbons, that hydroxyl group, which, by the way, organic chemists are kind of typically lazy and don't want to waste ink or time. And so when you draw OH, a lot of organic chemists will just leave the covalent bond out. It would be there. It's there. They just don't want to draw it because there's so many OH groups in things like sugars and alcohols. So what happens when you add an OH, you call that a hydroxyl group, and what it does is it turns any hydrocarbon you add it to into an alcohol. And so there are many different kinds of alcohols, but the kind you just built this guy right here is the kind you're thinking of. This is what you get from using yeast to ferment grain sugar or fruit sugar. This is, well, you know what you call it? You know your naming conventions. You know what the prefix for 2 carbons is, right? That's F. And this is an alcohol. So there's 2 ways to say it. This is either ethanol or ethyl alcohol. Both are correct. This is booze, basically, right? Or recently, hand sanitizer, because so much hand sanitizer is needed right now that isopropyl alcohol, which is the typical hand sanitizer alcohol, is run out, and they're having to use actual, distilled grain alcohol, ethyl alcohol for it. And they put something in it to make it so that it would make you sick if you drank it, because, people are people. And, yeah. So, that's what that is. Okay, next functional group. A little more complicated. Now we've got a double bond, and we haven't seen that yet. That's called a carboxyl group. Try doing that in the software once you've drawn it. What's interesting is with the physical kits, this means you have to start bending the bond. They have special flexible bonds for that. But in software, it's easier. You just click on double, and then click on the bond between the oxygen and the carbon. And you get that double bond there. And then you still got to tack another oxygen onto the end. But now what you've got is what we call an organic acid, ethanoic acid specifically. Pretty simple one, not that common. Common acids you might be familiar with are amino acids, make up proteins, right? Acetic acid, which is vinegar. So, carboxyl group makes something an organic acid. Speaking of amino acids, the carboxyl group is what makes it an acid. An amino group is what makes it an amino acid. If a chain of carbons has just an amino group on it, we call it an amine. That's just nitrogen. That's nitrogen with those hydrogens filling in those bonds. Last but not least, this is kind of like carboxyl without the hydroxyl. I know this is a lot of new names. This gets to be kind of alphabet soup, but that's all right. Carbonyl is just the double bonded O without the OH on the side. And when something has that functional group, we call it a ketone. Ketones will be the subject of a potential extra credit question of the week coming soon. I post those in classrooms sometimes, and the first few people to get them correct will get extra credit. So functional groups. Basic naming based on carbon chain length and what kind of bonds are there, and then functional groups, which change the names of those things in specific ways. Make them alcohols or acids or amines or ketones. Questions? All right, that was a lot. I'd like to formally announce that it is officially quiz season, meaning you can expect quizzes any day of the week when we've had new material. So be aware of that. And I have an assignment for you, which is a guided reading assignment. You will need your e-text. Real quick,